Hello learners, welcome back to week 5 of Financial Mathematics for Actuaries. We have incrementally built our foundations and right now we are comfortable with handling annuities. Annuities are of two types. One is immediate, another one is due, and we already know the trap of that annuity. Immediate doesn't mean immediately starting, immediate at the end of the period, and due is actually immediately starting. So we have, with this understanding, one can ponder on a question that what if these annuities don't end, and that is a question that we are going to tackle today, and it is called perpetuities, where the time period is not finite. So what we are setting the context for is from finite to infinite. See, for example, in weeks 1 to 4 our payments lasted for n years. So we know when this annuity is going to stop paying the investor. Correct. So what is happening? Your principal is essentially getting exhausted, or it is called amortized, and typical cases are home loan, which is mortgage, and car loan, all these things where you have to stop paying them. Correct. Now what if we want to invest in a fund and so that it will pay me forever, right? So payment should continue forever. And what if I can have a facility where principal is not touched and only interest that I get is consumed? Do we have such real life use cases? The answer is yes. The endowment funds that you see, or the stock investments which are paying dividends, those are called preferred stocks. All those are examples of use cases of perpetuities. So let us understand these perpetuities mathematically. So that brings us to today's roadmap, which is first we are visualizing the infinite stream, and while visualizing this infinite stream we visualize it as the vanishing tail. That brings us to the question, what makes this tail to vanish? That essentially means the present value calculation that we are doing with this V notation, that will make us that will give us the vanishing tail. That is where we will derive the formula for this infinite stream of payments using the fact that V raised to n converges to 0. And then we will relate to one of the fable which is called golden goose fable, and we will relate whatever this infinite stream is to this golden goose principle. And once we have understood this via this intuition of golden goose, we will apply them to the context of scholarship funds and preferred stocks, how to invest in preferred stocks. As usual, the reference mapping is very clear. We have Browerman, the mathematics of interest and credit, section 2.1, and Chan and Say, financial mathematics for actuaries, section 2.3. You should read these sections to have elaborate understanding on the topics that we are discussing today. So let us first visualize this infinite stream, and in this infinite stream you can see the infinite number of payments having finite value. Is it a paradox? The answer is not really, because as you can see the payments are going to diminish as time progresses. Why should this happen, right? So if you relate to our V notation that we discussed, so if you remember our discussion in weeks 1 and 2, our discussion was revolving around, if I am looking at one period forward, then, and if I want $1 at time period 1, then the amount that I will invest is V equal to 1 upon 1 plus I. So this was our V notation that we discussed, right? So now if you look at this V notation, this number is always going to be less than 1. So if I consider time period 1, if this V is considered for time period 1, I have 1 upon 1 plus I. But if I consider time periods 2, 3, let us say I consider time period 4, I have 1 upon 1 plus I raised to the power 4. What will happen? This number will be definitely smaller than this number, right? So, it will have this relationship, and once this is the relationship, this is the number that we need to carry forward. That is why you can see there is a layoff, or there is a reduction in the payments. So, for example, if you go to v to the power 100, that number is going to be very minimal, it is very close to 0. What does that mean? The present value of the payment that we are talking about, that is given by the notation v, is actually tending to 0. That means your distance payments are worth almost nothing today, and therefore my sum will always converge. Okay. So, this is the intuition that we are building from this visual anchor, and once this is set, we can do the mathematics behind it. So, where to start? We will simply start with our standard annuity formula for finite n. What we are calling for is this A angle n that we are discussing. This is annuity immediate. It has a formula 1 minus v raised to n upon I. Now, we are calling for this n to tend to infinity. As usual in mathematics, when we call for this n to tend to infinity, we will look at the numbers limit as n tending to infinity 1 minus v raised to n upon I, right. Okay. So, this particular thing for every n has some consequence. So, I will split this limit into two parts. First, limit as n tending to infinity of, you split the first part, 1 by I minus v raised to n by I, correct. So, now what will happen? Now, I know that this v raised to n actually tends to 0. So, this limit actually exists, okay. So, I can split it. So, what I will do, first thing, you look at this number, is it dependent on anything related to n? No. So, this limit does not make sense. So, this number 1 by I stands as is, minus what I am interested in is limit as n tending to infinity of v raised to n upon I. Okay. Is there anything dependent on n? This I is perfectly a constant. So, I can simply, again I will do simple trick, I will take away this I. Now, I am left with limit as n tending to infinity of v raised to n. But what is my v? I already know that v is 1 upon 1 plus I. So, what will happen to this? This number is always going to be less than 1. So, we know that if the number is less than 1 and I am raising it to the power n, this limit will eventually become 0. So, what I am left with is 1 by I minus 1 by I into 0, right. So, that means my final answer will be 1 by I, correct. So, that is what I have explained in printed form here. V is 1 upon 1 plus I, which is less than 1, as n tends to infinity, v raised to n tends to 0, and therefore, I can easily evaluate A infinity to be equal to 1 upon I, right. So, what is the case that we are handling? This A angle n represents immediate annuity, right. So, this particular formula that I derived represents immediate perpetuity or perpetuity immediate formula. Okay. So, this makes me think how to write a general formula for perpetuity for present value, where here I have done calculation with $1 in my mind. So, I will simply multiply by that, okay. So, my present value is equal to my annual payments divided by I. So, that is very clear now, that if I am putting $1 here, that is my annual payment, A infinity will give me 1 by I will give me the perpetuity for $1 put every every annual term. Okay, so the present value calculation is clear. Let us immediately apply this for a scholarship fund. Hmm. So somebody wants to establish a scholarship fund which is paying $10,000 per year forever. Hmm. Payment is at the end of year 1. Interest rate is 4%. The question is how much money the donor should put today in order to have this kind of scholarship fund. The answer is immediate. What is my target? Payment that is required is 10,000, right? So I will simply say my PMT is equal to $10,000. Then what is the interest rate that I have? So we will call for I, and I is 4%, so it's 0.04, correct? So do I know the present value? The answer is almost immediate, because if you go to the previous slide, this is the one, right? PMT I know I. So what I should do? I will simply take PMT by I, and that should give me my present value, correct? So let us calculate that, and this is so easy. It's 10,000 by 0.04, so 4 by 100, so that will give me something like 2,50,000. So division of 4 for 10,000 multiplied by 100, so it gives me 2,50,000. Okay, just check once again whether the calculation is correct. By multiplying by 4%, you should get back 10,000. Okay, so what is happening here? The interest actually covers your payment, okay, and the principal of 2,50,000 that you have kept is untouched. Okay, so this brings us to one of the interesting fables in our mythology, which is called Golden Goose Fable. What is a Golden Goose Fable? A farmer is gifted a golden goose. That golden goose lays a golden egg every day, right? As long as that golden goose survives, the farmer is certain to get the egg, right? So now that golden goose is your principal, okay, and the aim of this golden goose is to generate $PMT forever. That means it has to give you one egg forever, right? So now how will you generate that egg? For that, what should be the strength of that golden goose? That you have to determine, and that is given by the formula PMT is equal to P times I, which is similar to P is present value. So it's P times I, which implies present value must be PMT by I. We have already seen this. So what will this particular golden goose do? It will generate an interest of $I. This $I is always given away. It's consumed as a scholarship because we are giving this as a scholarship fund. However, as long as this principal remains untouched, we are safe. We can we can consume this egg from the golden goose as many times as we want, okay, with some certain frequency. Perfect. So now this completes the principle of perpetuity, and this is related to golden goose. What if somebody says, I don't want to wait even for one period? How can I handle it, right? So that is where the perpetuity due comes. That means the payment starts immediately. What is the difference? When I want the payment to start immediately, I need that much more capital that I need to pay. Okay, that's the only difference, right? So what happens if I consider, if we contrast this with immediate payment, we are allowing the interest to accumulate over one time period. Now we are not allowing that interest to accumulate over one period. So if you notice, the difference is exactly one time point, and that time point, when we were discussing this annuities, we said that whatever is my AN, I will multiply A angle N, I will multiply it with 1 plus I, and I will get A double dot n. If you remember that, then same thing should be applicable here also. Okay. So, let us figure out what is this. So, if this is n tending to infinity and both these limits exist, then this is 1 by I, which is my A infinity, correct. So, if I multiply this A infinity by 1 plus I, what I should get? I will get 1 by I plus 1, okay, and that this I am multiplying with 1 plus I, okay. So, this is nothing but A double dot infinity, right. So, as you can see, this is the formula that we have given. So, it is 1 plus 1 by I, right. However, if you do not simplify it this way and you keep it this way, which is basically 1 plus I upon I, what is this? This is equal to 1 by D. So, A infinity is nothing but 1 by D, okay. However, it is up to you whether you want to remember this formula. For me, it is always convenient to visualize this by multiplying with 1 plus I. So, that is the connection between 1 plus perpetuity due and perpetuity immediate. Okay. So, now that we have understood how to calculate perpetuity due, let us take one more application, which is in the stock market. We call it preferred stock. What is a preferred stock? You know, a stock pays a fixed dividend forever. That stock is called preferred stock. So, for example, if I want to invest in some preferred stock, I need to know whether it is worth investing or not, or whatever price I am going to buy, whether it is a good price or I am paying higher or lesser, right. So, that leads us to the following problem, which is, if a company X is paying you annual dividend of $5, I want my investment to reap the return of 8%, then what should be the fair price of this company X, stock of this company X, okay. So, now I have to bring in that golden goose principle. What is a golden goose here? What is the golden egg here? So, naturally the dividend is the golden egg, and the golden goose is the price that I am going to pay to buy that golden egg or to have that golden egg forever, right. And what depicts this, whether it is this price is the interest rate that I want in return, okay. So, what is the interest rate here? So, I need to essentially say what is the interest rate here. Interest rate here is 8%. So, I will call this as, okay. So, I will write it in decimal form 0.08, and what is the golden goose or PMT here? Okay, PMT is actually equal to dividend here, okay, and that dividend is $5, correct. And what should be the price, that price or the PV that we want to see? So, or PV, the price that I need to pay right now, that should be in question, right. So, with this we are set with our perpetuity formulation. We will simply put this price is equal to dividend by I, whether it is annuity due or annuity immediate. The moment you buy, the company may not pay, right. So, it is, there is a fixed time. So, it is not annuity due, it is a annuity immediate question or perpetuity immediate, because we are dealing with infinite time horizon, okay. So, that makes this formula clear. Now, it is just a matter of algebra. So, you substitute this 5 upon 0.08, this is the investment return that I want, and that comes out to be $62.5. So, I can buy this company X stock if I want this $5 return for $62.50. This is the fair price of the one. However, I want to show one more quick check how it reflects the rate of return, okay. If I want more rate of return, okay, if I want more rate of return, then what is your expectation? The price of the stock should go up or down. Will you pay more and buy the stock, or will you pay less and buy the stock? To ensure that that point is clear, let us look at, let us say rate of return becomes 10%. Okay, required return I want 10%. Then what will happen? I will simply divide 5 by 0.1 and then the price becomes 50. What does this mean? If I want higher rate of return, I should not be willing to pay higher prices. I should go for lower and lower prices, right? That is the best deal that I will get. Okay, so if my rate of return is high, I will not go for this particular stock. Okay, I will buy at lower and lower prices. That's the idea. So this is how you can discuss the sensitivity of this application of preferred stocks. Okay, now we have done this, we have understood the theory behind this. In exams you may need to use calculators, but there is one problem with calculators. The calculators do not have an infinity button. Okay, can you solve that problem? Yes, you can. What you do is you use the large value of n, and that value of n should resolve your problem, because let us say if you put n to be 4 times 9, okay, 9999, then what happens? This present value v raised to 999 is approximately equal to 0. So in your precision, this error is very negligible, and if you do that, then you might get correct answers. Okay. However, theory is there will be no rounding off errors. So you generally rely on theory, but this is the calculator trick that we can implement for scholarship problem. N is 4 times 9, interest rate was 4%, PMT was 10,000 with minus sign attached to it. Future value you put it as 0, then you calculate the present value, that should be 2,50,000. Okay, so this is very clear, and you can easily check on your calculator that this trick works. Okay, now let us understand this, that if I am not happy with payments that are happening annually, but I want the payments to happen monthly, quarterly, or any other period, what should be the trick? You know that slice method, denominator machine, so we will use that. So what we will do is, if the payments are due monthly, whatever we did for annuity, same thing applies here. Our numerator is always going to be total annual payment divided by the nominal interest rate that is given for that period. It's simple, just don't mix up the interest rates. You will certainly get the correct answer. So let us take one example. I have $100 per month forever, interest rate 6%, okay, and this is the effective interest rate that I have, right. So this is the effective interest rate I have. So my total annual payments, or that I need to withdraw from this, is 100 into 12, which is 1200. So now I will take this 6% interest rate and calculate the other interest rate, which is nominal interest rate, and that will give me that again that bridge equation you use. I will not repeat it. It's basically 1 plus I is equal to 1 plus Im by m raised to 12. In this case, that m was 12, this was m, so the Im was 12. So I will get this equation, and that is what is reflected here. Okay. Then you can easily calculate this I12 to be equal to 5.84%. So what is the next step? You use that rate, divide this by total annual payments, and you get the final answer, which turns out to be 20,544. Okay. Now we have understood perpetuities, we have done immediate and due perpetuities both together, and for that we understood that present value for immediate perpetuity is 1 by I. The payment starts at t is equal to 1 immediately at the end of first period. If you are dealing with due perpetuities, you need that one payment extra. So, the value is 1 plus 1 by I, or you can treat this as 1 by d, starts at t is equal to 0. The golden goose principle helps you in generating that interest. So, you have that golden goose which will give you the present value, you have that golden egg which is the PMT, and both of them are linked by the interest rate I, correct. The calculator trick that we need to do is use the largest value, largest 4-digit value. In this case we have taken 4 times 9, and once you use that value you will get effectively same answer. However, I will still stand by the claim, theoretical answer will be the most accurate answer. Okay. Next up, in the next class we will look at if these annuities are not at the period but flow continuously. Okay. So, it is like payments are flowing like a water. Okay. What are the use cases? It is like you are having a toll booth, okay, where you are collecting toll for a road. Every day, every customer that goes is paying you, right. So, that is a continuous payment stream, right. And what if we design continuous annuities? How will we handle them? That is the topic of our next lecture. See you in the next lecture. Thank you.